Four giant comets are erupting into life, one of them from beyond our solar system, hurtling toward a rare collision course with the Sun in 2025. Scientists call this century's first comet traffic jam, a cosmic event that's never been seen before. Could solar storms and alien chemistry reveal secrets hidden since the dawn of the solar system? Or leave us watching as these giants fragment before our eyes? The answer starts with why they're all waking up now. Astronomers have started calling it the first comet traffic jam of the century. Four giant comets, all active at once, are now converging on the inner solar system, a configuration so rare that even seasoned skywatchers struggle to find a historical parallel. The term might sound playful, but for scientists, it represents a remarkable opportunity and an urgent challenge. Comets are often described as icy leftovers from the solar system's earliest days, but when they approach the Sun, these frozen archives change dramatically. The process begins with sunlight reaching the comet's surface. Even at distances as far as Jupiter, the Sun's energy can penetrate the dark crust, heating up buried ices of carbon dioxide, carbon monoxide, and other volatile compounds. Unlike water, these ices vaporize at much lower temperatures, allowing some comets to wake up long before they cross Mars's orbit. As the heat triggers sublimation, jets of gas and dust erupt from the nucleus, forming the characteristic coma and tail that make comets visible even from millions of kilometers away. The 2025 traffic jam is not just about numbers. It's about the scale and timing of activity. Each comet is now entering a zone where solar energy is strong enough to drive rapid outgassing. At the same time, the Sun itself is at the peak of its 11-year cycle, unleashing more ultraviolet light and solar wind than at any point in the last decade. This combination means that the mechanisms driving cometary activity, sublimation, jet formation, and tail development, are now playing out in real time across four different objects, each with its own chemical fingerprint and orbital path. For the global astronomy community, the convergence has triggered a race to observe and analyze every phase of this awakening. Major observatories are coordinating schedules, while amateur astronomers track sudden outbursts and subtle changes in brightness. Data from ground-based telescopes, space missions, and even weather satellites are being pooled and shared at a pace rarely seen outside planetary defense exercises. The stakes are high. Every hour of observation could reveal clues about the origins of these comets, the chemistry of their ices, and the forces shaping their journeys toward the Sun. As the traffic jam unfolds, scientists are watching not just for spectacle, but for the secrets these giants might finally surrender. 3I/Atlas arrived from beyond the solar system, first spotted by the Atlas survey in Chile on July 1, 2025, and traced back in images to June 14. Its hyperbolic orbit, with an eccentricity above 6 and an inclination near 175 degrees, marks it as an interstellar visitor. Spectroscopy reveals a striking chemical makeup. Carbon dioxide dominates, with little water or iron, yet nickel vapor matches levels seen in local comets. For planetary scientists, 3Y/Atlas is a rare sample of material formed around another star, offering a direct look at chemistry shaped far from the Sun. C/2025 IR2 or SWAN reached perihelion on September 12, 2025. Its fading tail, now a ghost of its former self, leaves behind a detailed record of how solar heat and wind erode a comet's volatile layers. SWAN's slow decline, observed by professionals and amateurs alike, provides a baseline, a control for measuring the more dramatic changes seen in its companions. C/2025 A6, known as Lemon, draws attention for its twin jets, discovered by the Tenerife team. These jets, likely triggered as rotating patches of ice face sunlight, twist and spiral outward, sculpting Lemon's coma. The jet's behavior under solar glare promises new insight into how comet surfaces react to sudden heating and the relentless push of solar wind. C/2025 K1, or Atlas, is the unpredictable one. Its closest approach to the Sun comes on December 31st, 2025, placing it in the heart of solar activity. Though its composition remains under study, astronomers are alert for sudden outbursts, shifts in tail direction, or rapid brightening as K1/Atlas faces the Sun's full force. Together, these four comets, an interstellar outlier, a fading survivor, a jetting nucleus, and a risk-taker on a close pass, offer a rare chance to watch how different origins and chemistries play out under the same solar storm. Solar storms are rewriting comet tails in real time. As solar cycle 25 reaches its peak, the Sun's magnetic field is tangled and restless, sending out wave after wave of charged particles. When these gusts of solar wind and sudden coronal mass ejections sweep through the inner solar system, they slam into the comets now crowding the ecliptic. Each encounter acts as a natural experiment in plasma physics. On August 21st, 2025, a fast, full-halo coronal mass ejection erupted from the far side of the Sun. 3 days later, the ion tail of 3 I/Atlas snapped and faded, only to regrow as the solar wind calmed. This tail disconnection event, caught by SOHO and Stereo, wasn't just a visual spectacle. It revealed how the Sun's shifting magnetic fields can sever a comet's plasma tail in an instant, stripping away ions and forcing the tail to realign with the new direction of the interplanetary field. The same week, K1/Atlas and Lemon showed sudden kinks and ripples in their own tails, each responding to the shock front in its own way. For Swan, the fading survivor, a late November sector boundary crossing triggered a brief but dramatic detachment, captured in a single side-on frame. These events aren't random. Each comet, with its unique orbit and chemistry, serves as a probe, tracing the invisible structure of the solar wind. Scientists at ESA and NASA are piecing together a multi-point map using data from space-based solar monitors, ground-based telescopes, and even planetary orbiters. The upcoming passage of the Hera spacecraft through the predicted ion tail of 3/Atlas, sometime between October 25th and November 1st, offers a rare chance for in situ plasma measurements. If Hera's instruments are activated, it could record the magnetic draping and particle environment inside an interstellar comet's tail, something never directly sampled before. Magnetic reconnection, the process that snaps and reconnects field lines, lies at the heart of these tail events. Every coronal mass ejection comet collision is a test of how plasma and magnetic fields interact on a cosmic scale. The frequency and violence of these events in 2025 have turned the inner solar system into a living laboratory, with each comet's tail acting as both target and tracer for the Sun's restless energy. The next solar storm could bring the most dramatic tail disconnection yet, and with multiple comets in play, the scientific payoff grows with every new eruption. 3 I/Atlas is now hidden behind the Sun, but the data it left behind is rewriting the rules of comet science. Its trajectory alone defies local origins, an eccentricity greater than 6, an inclination near 175 degrees. This is not a wanderer from the Oort cloud. It's a visitor from another star, carrying the chemistry of a distant world. Spectra from the James Webb Space Telescope reveal a carbon dioxide to water ratio of 8:1, a value almost unheard of among solar system comets. Nickel vapor is present, but iron is conspicuously missing. The absence of iron, paired with a surplus of nickel, has left planetary scientists debating whether 3Y/Atlas formed in a carbon-rich, high metallicity environment, or if it's been chemically altered by billions of years in interstellar space. For planetary defense teams, the convergence of 4 active comets has become a real-world rehearsal. Tracking protocols, global data sharing, and rapid response drills are now routine, not because any of these objects threatens Earth, but because the unknowns are too large to ignore. The International Asteroid Warning Network is treating 3I/Atlas like any other unfamiliar object, monitoring its brightness, modeling fragmentation scenarios, and preparing for sudden changes. K1/Atlas, meanwhile, is approaching its own moment of truth. Its perihelion at just 0.3 astronomical units from the Sun puts it in the crosshairs of intense solar heating and tidal forces. Astronomers have watched similar comets break apart under this kind of stress, sometimes spectacularly, sometimes in silence. Models can't predict if K1/Atlas will survive the pass or fragment into a trail of icy debris. Skeptics at JPL and ESA caution against reading too much into apparent anomalies. They remind colleagues that rare doesn't mean unnatural, but even they admit that the sheer number of unanswered questions, especially about 3I/Atlas's chemistry and survival, makes this comet season unlike any other. As the Sun's activity peaks and the comets draw closer, the sense of anticipation is matched only by uncertainty. The next signal from 3I/Atlas, when it reappears in December, could confirm survival, reveal fragmentation, or deliver a new set of mysteries. In 2025, 4 giant comets, 3I/Atlas, Lemon, Swan, and K1/Atlas, were observed active at the same time, the first such event confirmed by NASA and the European Space Agency in over a century. Archival data from Atlas and Palomar established 3I/Atlas as only the 3rd known interstellar visitor, with a measured eccentricity above 6 and an inclination near 175 degrees. Spectroscopy from the James Webb Space Telescope revealed its coma is dominated by carbon dioxide, with nickel detected but iron notably absent. Scientists documented rapid tail disconnections during solar storms and the potential for K1/Atlas to fragment near perihelion at 0.33 astronomical units. Yet key questions remain. The full fate of 3I/Atlas as it passes behind the Sun is still unknown, and the origins of its unusual chemistry are not fully understood. What is clear from this unprecedented convergence is that cometary behavior under intense solar activity offers direct insight into both solar system and interstellar processes, a rare chance for discovery grounded in observation and data.